Now, this is a chapter where you find a lot of uh, strange inaccuracies in the definitions sometimes, and so we'll have to work quite a bit on that. But before that, let me tell you that I did most of the preparation of this for this talk on October 31st, and this was Halloween. And so I think it's a good idea to introduce you to my companion who always writes all the manuscripts for me. So here it is, it comes up here. Uh, and I can say uh, this really is, uh, yeah, it's my ghostwriter. And uh, so you write all my manuscripts? Yes, yes, yes. But you pay me to less. Yes, yes, yes. Shut up, man. Uh, so I'll put him down here and let's continue. Now, if you think that the nonsense here was enough, you will hear more nonsense as time goes on. But this comes from the fact that we have problems with the concept of polynomials quite often. So suppose you write down a typical polynomial, maybe 3 minus 4x plus x squared. Uh, then you can question what's the x? And you can say, well, sometimes people call x a variable. Now that cannot really be because variables are named for arguments for functions, and we don't have a function here, we have a polynomial. That the polynomial is sometimes also a function that comes later, and we have to wait for that. Now we are simply heading for polynomials alone. So another thing is people call it a symbol. But if it's a symbol, can you please tell me how to square a symbol or how to multiply a symbol with -4? That's not defined. The same happens if you say it's an indeterminate. Because that's again the same problem. If you have an indeterminate, what's that, and how can you multiply an indeterminate with itself and so on? In mathematics, we do have some axioms, we have definitions, we have theorems, but I have never seen the definition of a symbol, definition of an indeterminate in a good way, and so none of that work out well, and we should forget about that. That means that we have the question, what is x really? What's the nature of x? So what we need is better to make a new start. We can say that this polynomial here is in fact determined by the sequence 3 minus 4 and 1. Yeah, and this is nice because that is, if you take it as a sequence, the concept of the sequence is really correctly defined, usually in the literature. And so you can say, okay, a polynomial is simply a finite sequence of elements from, let's say, from some commutative ring R with identity at the moment. Sometimes, however, if we add them, well, we can add two polynomials in the same way as we add sequences, but sometimes a polynomial, one of them is longer than the other one. And so it's a good idea to say we identify this with the polynomial 3 minus 4, 1, 0, 0, and so on. And take this simply as an abbreviation of this. Abbreviation, one might argue or ask a question, why is abbreviation such a long name if it's an abbreviation? So we have this, and these are simply sequences which finally end up with 0. So there's a last term here, which is unequal to 0. And so it's terminated here. In fact, that's another good question. If flying is so safe, why do people call the departure building a terminal? That sounds so terrible. Okay, so if we take this, where is this from? Well, this you take it if it starts from a ring R, from R, direct sum with R, direct sum with R, and so on, the infinite direct sum. And this is just defined as a set of all sequences which are equal to 0, where the components are equal to 0 from a certain point on. Yeah, and then the definition of a polynomial would be the following, that if we have two sequences, okay, let's make a definition. A polynomial is simply a sequence of elements of R in the sense that they finally end up with zeros. So the addition is the same as we add polynomials in the old sense, and the multiplication is this, that 2a sub 0, a sub 1, a sub 2, and so on, times b sub 0, b1, and so on. This will be c sub 0, c sub 1, such that c sub I is simply the sum of all elements a sub k times b sub I minus k, where k runs from 0 to I. The usual convolution of sequences. And so you see in this sense that you, I think the, don't like the light here. No, kitchen, okay. I think the light might be better now. And so you have this definition. And the good thing is, if you define a certain sequence, namely the sequence 0, 1, and if you define this by x, what would be 0, 1 times 0, 1? So by this definition of multiplication, it's 0 times 0 is 0. 0 times 1 plus 1 times 0 is again 0. And 1 times 1 is 1. And you see that things develop nicely, because that what we have here is just the x squared. And if you have, excuse me, if you have x squared here, you know what x to the third is and so on. And that means that you can, in fact, write now the sequence a sub naught, a sub 1, and so on as a sub naught times 1 plus a sub 1 times x plus a sub 2 times x squared, and so on. And you see, the world is wonderful here. We get back to the old definition of a polynomial, but now we know what x is. X is not a variable, it's not a symbol, it's not an indeterminate. X is a special polynomial, a special sequence, the sequence 0, 1. So you might say this is very academic to call this polynomials, or to rename the polynomials and call them now sequences, because they lead to a similar thing. But it's not so academic at all. Excuse me a moment. Not academic at all, because, for instance, in systems theory or in automata theory, you often have input sequences. So you have a sequence like that here. And this might be an input sequence. And we can now say, instead of saying a sequence, we can also say this is a polynomial P. And it's meant in this way. Usually a sub naught is the input at time naught. So right now, A1 is the input say 1 minute later. A2 is the input 2 minutes later, and so on. And it's important in systems theory to consider also shifted sequences which start 1 minute later. So that would be, with one time shift, would be 0, and then a sub 0, a sub 1, and so on. So a sub 0 comes in at minute number 1 and not immediately. And you see that you can simply represent this as x times p. So you don't have to introduce a shift operator, as it's often done in systems and automata theory. You can simply consider them as polynomials, and then you multiply the polynomials with x, and you know, of course, what happens if you have a longer time shift, and you know what happens if you have an overlap of this input sequence and this input sequence. It's just a sum of this, so it's just p plus 1 times p plus x times p, so it's 1 plus x times p. And so you see that the possible shifts and overlaps they act on the set of polynomials here, and this in a very, very convenient way, where you don't have to come up with complicated operators. But that all works nicely if R is a commutative ring with identity. What happens if R is, say, just a ring, or a ring with identity but not necessarily commutative? And then you see sometimes in the literature the very strange formulations. For instance, if we don't have commutativity, uh, we might consider 3 times x or x times 3, and we might ask, are these the same? And sometimes people write in papers, we consider the polynomials over a non-commutative ring, and we want the x to commute with the elements of R, or we don't want to commute. So we have commutative, uh, sometimes they say variables, but they are not variables. And who decides if this is true or not? And well, who can make a decision? Is it the Secretary General of the United Nations, or is it the Pope who says this is the same or not? Or can you decide? So it means we have to dig a little bit deeper to find out what really goes on here. And the thing is that we again better have a new start. So let's restart again. Suppose we have a class of rings. Let C be a class of rings. They might be commutative, have an identity or not. All is possible. And we can say that if we look at a typical polynomial, it's made up of the elements of the ring, the a sub I, and it's made up of x. And we make all kinds of operations which we can do to add, to multiply these things. So for an informal definition might be a polynomial that's everything which can be built up from polynomial over a ring R, from elements of R, union with some set X of what we think of indeterminates from that, and also, yeah. So that sounds like that a polynomial is something which is generated from elements of R and elements of X. But generated is not a good word, because you can generate a substructure in an algebraic structure if this is all contained in a big upper algebra. But here we have nothing. We are out in the free space. We have an R, we have an X. We have nothing which contains R and X at the moment. And so we cannot say that's generated. Also, it doesn't really answer the question if again, if x, 3x is x times 3. Because both of them can be generated or can be composed with these elements, but it doesn't tell you how to work with those. And can you use distributivity? Obviously, yes, if you're in the case of rings. Commutativity, maybe not, because you might also consider polynomials over non-commutative rings. And so you have to add something that the equality That's a delicate question. What is the quantity of two polynomials, say P and Q? If, well, let's say, for instance, what happens with A plus B times X times X? Is this the same as A times X plus B times X squared? Well, if we have the distributive law, then we can say this. And so we have the following idea. If we are working in the area of rings, we should have both distributive laws at hand. And so we can say two polynomials are the same if the first one can be transferred to the second polynomial using the laws. Yeah. Yeah, but now you see that gives perhaps an idea of what a polynomial might be, something which is made out of R and X, and the union, and the two are equal if one can transfer the other one using the laws in C. And you see that we are again in a mess because we have a lot of undefined concepts now. We have this here can be built up. What does that mean? Then the equality, if it can be transferred, what does it mean, transferred? And what means the laws in C? What is a law? And so we have a lot of undefined questions. And the goal of today is to make these things here more precise. The advantage of this is that we get a big reward at the end because we'll see that we can define polynomials not only over rings, but over any type of algebraic structures. And that will give rise to a lot of interesting type of near-rings, which are presently studied quite intensively. So if we look at the last line here, using the laws in C, we have to find what the law is, and we have to find out what the laws of a class of rings are. And we might, well, some laws, we have things like associativity or so in mind, perhaps, or distributivity or commutativity. They might hold in some rings in C, and they might not hold in other rings in C. And so back to the start again. We have the next restart. Okay, let's first work on the thing with the build-up. And it starts a bit complicated, perhaps at the beginning, but very soon you will know, see what's behind that. Suppose we have a set. We start with the set omega and write this as circle I I in some index set I. That's just a set, nothing else anymore. And we start with another set, n, and we denote this by n sub I in the same index set. And in this case, we want more. We want that the n sub I are elements in the natural numbers or zero. So we can say for every symbol, for every element circle I here, we have a natural number or zero n sub I. Yeah, that's pretty abstract and hard to find out what's going on here. Just a notation, we call n sub I also the absolute value or so of O sub I, and call this the arity of O sub I. At the moment, it's very abstract, but even on this abstract level, we can do a lot of things. We need another ingredient plus a set x. That will be our x's as before. Call them x sub j, j and j. And from that, we'll build up what we want to have for polynomials. And to avoid some pathological cases, we want additionally that the sets omega, n, and x are mutually distinct. So the next thing is we build up so-called words from this context. And do it inductively. We say words have a rank of rank 0. These words are easy. These are the whole circle I of arity 0, which is possible by this here, and all x sub j. These are words of rank 0, and if you have this, then the loop starts. If you have words of rank k plus 1, what are those? These are all of the form composed with I of W1, W2, and so on, according to the arity of circle I. Well, these are words of rank less or equal to k. If the arity of O sub I is greater or equal to 1. Otherwise, there's nothing to put in here. So we can inductively build up words, starting from very simple words, things of arity 0 or the x sub j, And if we make strings, this has no meaning in it. It's just a string. And it will get a meaning in a few minutes. So what can you say about the words? All words are obviously then given by finite sequences, by finite strings of these uh, circle i's and the elements of xj and composition uh, yeah compositions of this type. Uh, so you get more and more complicated strings, and the equality is strict equality. So we uh, consider two words to be the same if and only if they look exactly the same. Yeah, but now we are still far away from the concept of a polynomial, it looks like. But let's see. What we can do now is to say that we define a law. And let's think of a law something like commutativity. X1 times X2 is X2 times X1. We cannot write this as equality because we don't know if this holds or not. And to write an equality sign is a very bad idea here. But you can say you consider the law of commutativity of multiplication, for instance, uh, or you characterize it in the way that you say it's just a pair, and you think of x1, x2, comma, x2, x1. So we can say that a law is just a pair of words. We once at Linz had uh, an invited speaker from abroad, and he lectured just about this. And the title of his talk was uh, 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 Laws in Free Structures. So it was announced all over the university. And when the lecture started, more than half of the audience were students of law, and they had no idea what was going on in the laws of free uh, the laws of free structures, and they were completely bewildered. That was a big misunderstanding. Now, so we have the thing of laws now, and we can hope to start to proceed in a nice way. And the next thing is what something which you are really waiting for to get algebras of a certain type. So I can promise you that was the last necessary restart. And now let's say if A is a set, and each circle I is a map from A to the nth of I into A, Remember, for circle I, we have made no assumptions at all, just a set of elements. And where n sub I is just the arity of O sub I, of course, then we say that we have omega, that each omega sub I is an n-ary operation on A. Each O sub I is an, let's see, O sub I ary operation on A. And that's more familiar than it has been before. And we can now say that if we have A together with this omega for operation, and so these are not small O's, but they are small omegas, very small omegas, that this is an algebraic structure or simply a universal algebra. Of type, I've called it N before over that. So it's an algebra of type N. And we immediately think of, say, things like groups, rings, and so on. Maybe we start with if, say, omega is just the set of a single circle, and the arity of this is equal to 2, then we get A together with an two-ary operation is the usual type of operation we have in groups, rings, and so on. And so if we have this, what we get is a typical, it's not a semigroup, but we don't have associativity yet. What we have is that characterizes all groupoids. Now, groupoids are basically nothing. They are a set with a binary operation, and they don't have it doesn't have to be associative or anything. It's just of this way. Now, so especially if you speak of semigroups, you speak of algebras of type 2. So semigroups would be algebras of type. Yeah, we also write it simply, perhaps as 2. It's an abuse of notation. It should be a circle of arity 2. But as I mentioned, not every algebra of type 2 is a semigroup. We still need associativity. We still need to have the thing with the laws implemented more closely. The next thing is non-trivial now. What about groups? These are algebras of type, yeah, you can also say of type 2, as before. If you say a group is a set together with a binary operation, say multiplication, and let that be. But in groups, you also have a unary operation, namely forming the inverse. So it might also be considered as type 2 and 1, where this would be composition 1, this would be composition number 2, and composition number 2 has arity 1, so it goes from A to A, such that each A is turned into its inverse if we use multiplicative notation. So that's a typical unary operation, and we might consider this as well. However, you can even add something more. You can write it as type 2, 1, and 0. And what is 0? That's the third operation, circle 3. And circle 3 would go from A to the zeroth power. The zeroth power of a set. What should that be? Into A. And the zeroth power of a set A, let's put it down here, is the set consisting of the empty set, a one element set. So we only have to say this empty set should go into, say, let's call it the neutral element of A, of the group A. And so you have the choice how to consider a group as an algebra of type 2, or that you take the inversion also into account, or that you can take the determination of the neutral element into account. So at the moment, we don't know what's the best thing. We can use all these three, but very soon it will turn out that it's much, much better to take the third version because of a reason which will come up immediately. An interesting thing is, if we go from groups to another structure, namely, if we go to vector spaces, maybe I can. So if A is a vector space over a field F, how can you take this into this framework? Well, first of all, A with respect to addition is an algebra of type 2 or 2-1 or 2-1-0, as we have seen before. And I told you that the third is the much, much better version. So we take it as a algebra of type 2-1-0 for addition. And now we have the thing with taking a vector and multiply it with some lambda in F. And you can do it in the following way. You can take circle lambda as a unary operation from A to A, taking each, let's call it now perhaps V for vector space, into lambda times V. And so you see that building the lambda times vectors, that also can be modeled as an operation, namely as a unary operation. In fact, we have a lot of unary operation for every element lambda in F. And so we perhaps can say this union with all lambda, where lambda is in F. I've now mixed the notation of families and sets. It's better to use sets alone, but that has been so common. So you see, we can very well have, if F is an infinite field, we can have infinitely many operations at hand, because we can simply make every element in F into a unary operation circle sub lambda. Now, yeah, question 8. Look for some possible characterizations of the type of Boolean algebras. Boolean algebras are also very important with respect to polynomials, because you know that polynomials over Boolean algebras are very useful in applications like building electrical designs and switching circuits and things like that. So good. The way to proceed now is the following. Suppose we have a certain type T and a corresponding family of operations that we take now as the class, like a class of rings we had before, namely C of T of a type T is the set, or better not set, is the class of all algebras A omega of type T. One has to be careful here, because the class of all algebras is usually not a set. Simply take the following example. Omega can be void at all, so there are no operations there. We are just speaking of sets, and then this would be the set of all sets. And you know that this is strictly forbidden. You don't even are allowed to think of that. And so C of T would be the class of all algebras of type T. Now we can say what we had before. C of, say, let's again a use of notation, it would be of the set of 2. This is the class of all corporates. And so on. Yeah, now we are in fact partly happy what we have got so far, because we have class of algebras of the same type. Usually we don't want to mix the type, we don't want to have a say groups and vector spaces which are not related at hand. But what is still missing is something like in here. You want to have something like associativity. How can you interpret a law now in this context when A is a set and each circle A is an array operation on A? Now we have defined laws already. These are just pairs of words. So what can we think of a law, namely a pair of two words, W1, W2, and maybe it's a good idea to make an example first. Let's take this example, the algebras of type 2. So let the omega be simply the circle of arity 2. What would be a possible word? One possible word would be a circle, and we have to take x1, x2. So this are two words of how did I call it? Frank 1, no, Frank 0. And so if we do this, we have a typical word of Frank 1 here. And another possible word would be circle x2, x1. And you see that we can come closer to the concept, say, of commutativity if we say we have a law now of the type circle x1, x2, comma circle of x2, x1. And it still doesn't look very familiar, so it's better to use infix notation. And we say the law here is runs as x1 circle x2, comma x2 circle x1. Yeah, now we are coming pretty close to commutativity, and the same thing you can imagine goes with associativity and other things, idempotency and so on. All what we have to do now is to find out that we take this law with the more comfortable infix notation, and to get something like a definition for that this law holds in some algebra or not, which makes this algebra then commutative or not. Yeah, so hard to say. What should we take here now? Well, a good idea might be to say this law holds in, say, in the algebra or in a groupoid, if it's always true. But always true is not yet at hand, because here we have simply two words, and they can never be the same because they look different, and so they are always unequal. And hence, we want to replace the x sub i's by elements of this algebra. That's the most meaningful thing we can have here. So we replace x1, x2 by elements of our groupoid. And if this and this always give the same element, then we say that this law holds in this groupoid, which makes it into a commutative groupoid. What does it mean to replace? Well, it's easily seen. You can, if you have, say, x1 composed with x2, you can make this word into a function by replacing x1, x2 by elements of the algebra. And this we call the induced word function. if you have a word which contains a word containing, say, x1, x2, up to x sub k, then we can make a function out of that, the induced function w bar, and we have to add a, which algebra we mean, because we have to test this in a special algebra A. This would be a function from a to the k into a, such that each element x sub 1, x sub 2, up to x sub k are replaced by arbitrary elements in a to the k. So you take any k tuple of elements in a to the k and replace x1 by a1, x2 by a2, and so on. And you must get an element out of a again, because we have operations which are n-ary, and they always start in some power of a and end in a itself. And so that's the induced word function. And we can now say what the law is. This law, we can say, holds in an algebra A. Let's add the omega of this. If now the big thing is that we can characterize it very easily if W1, let's say V and W, to if V in A has the same induced word function as W in A. So it was quite complicated. I apologize for that. It's not easy because it really isn't easy, but it's now an approach to polynomials which is correctly defined in all points, and you can say what a law is. A law holds in an algebra if this is true, and if you think back to groupoids, a law holds in a special groupoid A if, yeah, if this groupoid is commutative. So it's exactly what we have in mind, or had in mind, all the time. And we can say that the associative law that would be W1, comma, composed, well, let's simply write the x1, x2, x3, comma, x1, x2, x3. This law holds exactly if the groupoid is a semigroup. Now, that's good that we have to these things in mind. The commutative law, I've mentioned this, distributive law, all things like that have the can be expressed by pairs of words. And you might ask, if you get bolder perhaps, what about other things? Say the invertibility. Uh, isn't that also a condition which falls under this laws? Well, you see that for a law you have to have that this holds for all x1, x2, x3 if they are replaced by elements in A. And invertibility, say in a field, means that for all elements uh, which are not a zero, there exists another element which is the inverse, and so on. And so you have an existence quantifier around, but maybe that can be overcome. Maybe we find some laws which also can characterize, say, the invertibility in a field or of elements. Uh, what about finiteness? Can we find a certain collection of laws which characterize if an algebra is finite or not? It's very hard to tell at this point, but it will become much, much easier in a few moments. But before I proceed, uh, let me ask, is Gerhard Betsch around? Is he only a part uh, of the audience? Doesn't seem that way. Otherwise, that he could have given his talk now, but so we'll postpone it to next time.
He's not here.
Excuse me?
He's not here.
He's not here. Okay, thank you. Yeah. The next definition is very, very nice and interesting, and very successful. Let L be a set of laws. Can be a small set, a large set, and then we define the class of L, C of L, as, yeah, and we must take the perhaps the type T there as well. That's the class of all algebras, a omega of type T, such that this law, such that all laws of L hold in A omega. So now you take the other approach from the other side. You start with a certain type, let's say the type 2 again as before. Take L, the laws, perhaps associativity and commutativity. Then this will be the class of all group weights, such that associativity and commutativity holds there. And this is just the class of all commutative semigroups. And so it's very nice to characterize classes of algebras which are in some way defined by equations like associativity. The equations, I don't want to speak of equations right now, it will come, but these are just laws which hold in all of these uh, uh, algebras. We call this here a variety of algebras. So a variety of algebras is a class of algebras of the same type, such that all laws there can be characterized by a set of laws. And so one can say in some way a variety is a class of algebraic structures which can be defined by equations in a loose sense. This becomes less loose if we uh, uh, mention a famous result of the 30s, which gives another characterization of a variety. And this is a very famous theorem of Birkhoff. A class of algebras of the same type is a variety if and only if. And this holds like that. See a class of algebras of the same type. And C is a variety if and only if C is closed with respect to forming subalgebras, homomorphic images, and direct products. I haven't defined subalgebras, homomorphisms between algebras, because they run in the same way as you are used to those. Direct products the same. And here I mean unrestricted direct products. So not only direct sums, as we had before, direct products of arbitrary many components. That means if you have a class of algebras which is closed with respect to these three items, then you can be sure that they can be defined by equations, that you will find a set of laws which characterizes exactly this class. And this is a very mighty theorem, and the proof is far from being trivial. You have to apply Zorn's lemma infinitely often in the proof. And so it really says quite a lot. It says that it's the same if we say a class is closed with respect to these things, or if we say it's defined by equations. Now, from that, we get a lot of examples and counterexamples. So examples of varieties, let's call it AB, the class of abelian groups. Here it's easy to argue the class of abelian groups is defined by laws, namely associativity and commutativity. And you can also say subalgebras of groups are groups again. Hold on, maybe not. What is the, suppose if the a group is an algebra A only of type 2. A subalgebra is something which is closed with respect to, say, this multiplication or this addition. So we would have this case that, for instance, the natural numbers is a subalgebra. I use this notation here of the integers. But you see, it's not a group anymore. The only thing you have to be sure to be closed with respect to addition. That is the case, but it's not the case here. And what about the of type 2, 1 with the invertible condition? It also means that you have not necessarily the unit element included. And so if you recall the three possibilities of defining a group as an algebra of type 2 or 2, 1 or 2, 1, 0, the first two are not very good because as subalgebras you get something strange out of it, and you want to stay in the area of groups. And so you have to be very careful that you don't fall out of this class. That means that this is much better. What about class of appealing groups? Or other example of is N, the class of all nearings. It's also easy. They are defined by one distributive law and so on. What would be a say a counterexample? A class of algebras which is not a variety. Let's take fields. The class of all fields we have mentioned before. It's not quite easy to decide if you can make the invertibility of all non-zero elements if you can characterize this by a set of laws. But Birkhoff's theorem allows us to use another check. Is it closed with respect to forming subalgebras? Well, subalgebras of fields, maybe we can do it in some way that we get subfields exactly out. What about homomorphic images? Now that's a disaster. If you have a field, the only homomorphic image is a one-element ring, and that's not a field anymore. So you fall out here, and you fall out with direct products. Even the direct product of two fields is not a field anymore. It has lots of zero divisors. And so we see that the invertibility of non-zero elements cannot be characterized by laws. What about finite groups? Can finiteness be characterized by laws? No. Again, the third killer here is the thing with direct products. Even if you have small, say, groups, set 2, if you take infinitely many of them, the direct product will be infinite, and you're out of this area. And so you see that this is easy then to work out if some conditions can be characterized by laws or not. And the same further examples, for instance, all zero-symmetric nearings. That's a law. And or all constant nearings. So you get a lot of examples of good classes of structures, and you get some examples of bad structures which are not varieties anymore. By the way, be careful about the name variety. the name variety is also used in algebra in some other contexts, namely for solutions of the equations of polynomial equations of higher order. The solution set is in algebraic geometry also called a variety, and this causes quite a bit of confusion. So let me give a question number 9. Find a variety inside of the variety of abelian groups. And I mean strictly inside. So as say a subvariety, a class of abelian groups, which is not all abelian groups and not the class consisting of this the one element group, which is a variety and which can characterized be by laws in this sense. So you might say, okay, what we have done is now looking at characterizing algebras or classes of algebras, but we still not have arrived at polynomials. Next time. Next time is now next week. Same time, same station. Howdy. So thank you very much, and hope you will come back again. Bye-bye, bye-bye as well. And have a good week and stay healthy. See you next
Bye.
week. Bye-bye.
Bye. Your ghostwriter.
The ghostwriter, yes.
Okay.
Oh, it's a really ghost, yeah.
Yeah.
So bye-bye.
Bye.